Good afternoon. My name is Ng Terry, student ID 0382553. Today I'll be presenting my analysis for assignment 1 of Thermofluid Engineering 2, the design and analysis of an air conditioning system for a tropical climate building in Malaysia. I'll be covering question 1 and 2, walking through the full psychometric analysis and energy comparison. Okay, let's begin. Here's the structure of my presentation. I have 7 sections. I'll start with the problem setup and my design justification, then work through question 1 in 3 parts: outdoor air characterization, the immediate state selection, and the full calculation. After that, I'll cover question 2 of the mixed air system and finish with the conclusion. Okay. Problem setup and design choices. For the outdoor design conditions, I selected T equals 33 degrees Celsius of 80% relative humidity. This sits in the middle of the given range of 28 to 37 degrees and 75 to 85% RH, and it represents the typical Malaysia peak afternoon condition. Consistent with Map Malaysia records and ASHRAE climate data for Kuala Lumpur. For the indoor comfort target, I choose T equals 24 degrees at 55% relative humidity. This falls within the ASHRAE 55 2020 thermal comfort envelope of 23 to 26 degrees and 30 to 60% RH, and aligns with the CIBSE Guide A recommendations for tropical climates. The resulting dew point of 14.4 degrees ensure occupants won't feel clammy. The AHU operates in 2 stages as shown at the bottom. Outdoor air enters the cooling coil to be cooled and dehumidified, then passes through the reheat coil before being supplied to the room at 24 degrees. Question 1.1, Governing equations. To fully characterize the outdoor air at state 1, I applied 5 psychometric equations of 101.325 kilopascals. Step 1 is using the Tanton saturation pressure formula. The saturation pressure at 33 degrees is 5.030 kilopascals. And step 2 is the specific humidity formula gives omega equal 25.72 grams per kilogram of dry air. This is an extremely high moisture content. And step 3 is the specific enthalpy works out to 99.11 kilojoules per kilogram. Step 4 is the dew point from the Magnus inverse formula is 29.08 degrees Celsius. This is the critical value on this slide. It means any core surface cooler than 29 degrees will immediately start condensing moisture, so dehumidification is physically unavoidable. Step 5 is a specific volume is 0.9030 cubic meters per kilogram, which I'll use to convert the volume flow into mass flow rate. The constant U's are shown at the bottom, where CPA equals to 1006, CPV equals to 1.86, and yeah. Slide 5. Okay. This slide summarizes all 8 psychometric properties of the outdoor air. The table on the left shows the full results. The 3 most important values are the specific humidity of 25.72 grams per kilogram, the enthalpy of 99.11, and the dew point of 29.08 degrees. On the psychometric chart on the right, you can see state 1 in the upper right, hot and very humid. State 2 after cooling coil is down near the saturation curve on the left. State 3, our supply target, is in the comfortable middle region. The key insight here, the outdoor enthalpy of 99.11 is nearly double our indoor target of 50.2 kilojoules per kilogram. And since the dew point of 29.08 degrees is higher than our supply temperature of 24 degrees, dehumidification is completely unavoidable. This slide explains how I selected state 2. The condition of air leaving the cooling coil. 3 constraints govern this decision. Constraint 1 is the apparatus dew point. The ADP is the core surface temperature at which the leaving air reaches 100% saturation. I need the living air to have the same specific humidity as my supply target, 10.24 grams per kilogram. Solving omega saturation equals 10.24 gives TADP 14.4 degrees Celsius. That's the minimum cost temperature needed. Constraint 2, the moisture balance. The reheat stage adds absolute no moisture. It is purely sensible heating, so omega must equal to omega at 10.24 grams per kilogram. This means the cooling coil must remove delta omega equals 25.72 minus 10.24 equals to 15.48 grams per kilogram, which is over 16% of the incoming moisture. Constraint 3 is a freeze prevention. Chilled water coil runs at 6 to 12 degrees. If the living air drops below 5 to 7 degrees, frost forms on the coil fins, blocking airflow. Setting T at 14.4 degrees gives a comfortable safety margin above that freeze risk zone. Based on all three constraints, the decision is state 2 is T equals to 14.4, omega 10.24, and enthalpy 40.37. Mass flow rate and moisture removal rate. Now for the actual calculations, mass flow rate, the volume is 120 cubic meters per meter per minute at state 1 condition, dividing by V1 equals to 0.9030 gives 132.89 kg per minute or 2.21 kg per second. And moisture removal rate apply a steady flow mass balance on water vapor. Mass flow times the difference in specific humidity, which is 132.89 times 0.01548, gives 2.058 kilograms of water per minute, which equals 34.3 grams per second of liquid condensation draining off the coil. The comparison table at the bottom is important. Notice that omega equals omega, both are 10.24 grams per kilogram. This confirms that the reheat stage is purely sensible. No moist no moisture is added back. The temperature and relative humidity change, but the specific humidity remains fixed through the reheat coil. Now the heat load calculations, both using the first law of thermodynamics for an open system for at steady state. Cooling coil state 1 to state 2, the formula includes a correction for the condensate leaving the system. The condensate carries energy, H equals to Cp water times T equals 4.186 times 18.4, giving 90.28 kilojoules per kilogram. Substituting in 2.215 times the bracket 58.74 minus 0.93, which is 57.81, gives the cooling load of 128.0 kilowatts. And kept the condensate correction term for rigor. It's small at 0.93, but it's physically correct. Reheat coil state 2 to state 3 is purely sensible. Omega stays fixed at 10.24. The load is simply 2.15 times H minus H2 equals 2.215 times 9.84, giving a value of 21.8 kilowatts. The AHU process flow diagram at the bottom shows the complete system. Outdoor air enters the cooling coil, moisture condenses and drains off, then the conditioned air is reheated before being supplied to the room. Okay, so the summary. Here's a complete summary for question 1. The 4 key results are dry air mass of 2.215 kilojoules per second, moisture removal of 2.058 kilograms per minute, cooling coil load of 128 kilowatts, the reheat load of 21.8 kilowatts, the total AHU load for the 100% fresh air system is 149.8 kilowatts. On the process path at the bottom, stage 1 goes through the cooling coil to stage 2 via a diagonal path on a psychometric chart, removing both sensible and latent heat simultaneously. Then from stage 2 to stage 3 is a horizontal line. Only temperature rises, omega stays fixed at 10.24. Okay. So now we will move on to question 2. Moving to question 2, instead of 100% outdoor air, the facility managers propose a mixed system, 30% outdoor air at 36 cubic meters per minute and 70% recirculated air, room air at 36 cubic per meter per minute and 70% recirculated air at 84 cubic meter per minute. This mix diabatically in the mixing box before entering the cooling coil. The core question is, does this reduce the cooling load and what are the trade-offs? That's exactly what I'll calculate now. Three steps to find the mixed air state entering the coil. Step 1, mass flow rate. I calculate each stream separately because they are at different temperatures and therefore different specific volumes. Outdoor air, 36 divided by 0.9030 equals 39.87 kilograms per minute. And return air is 84 divided by 0.8555 equals 98.19 kilograms per minute. Total mixed mass flow is 138.05 kilograms per minute. This step is important using separate specific volumes, not just proportioning the volume flows in the rigorous approach. Step 2 is mix specific humidity from the moisture mass balance. The numerator is 39.87 times 0.02572 plus 98.19 times 0.019024, giving 2.0308. Divided by 138.05, the result is omega mix of 14.71 grams per kilogram, much lower than the outdoor air of 25.72. Step 3 is mix enthalpy and temperature. The enthalpy balance gives a value of 64.33 kilojoules per kilogram. Inverting the enthalpy equation gives the temperature of 26.65 degrees Celsius at 67% relative humidity. This is the table. Now the cooling load for the mixed air system, the moisture difference from the mixed state to state 2 is only 4.447 gram per kilogram compared to 15.48 of the 100% outdoor air case. Applying the same first law of formula, 2.301 times 23.69 gives a value of 54.5 kilowatts. The saving is 128.0 minus 54.5, which equals to 73.5 kilowatts, a 57.4% reduction in the cooling load. As shown in a comparison table, the total AHU load falls from 149.8 to around 77 kilowatts, roughly a 48 to 55% reduction. But there are important trade-offs to discuss. On the benefit side, on the benefit side, 73.5 kilowatts saved, approximately 735 kilowatt hour per day for a 10-hour operation, lower operating costs and reduced carbon footprint. On the risk side, only 30% is fresh air, so CO2 builds up faster. We need MERV13 or HEPA filtration in the return duct. We must verify against ASHRAE 62.1 minimum fresh air rate per person, and CO2 sensors with demand-controlled ventilation are strongly recommended. The mixed air system is correct engineering choice, but only with proper filtration and monitoring in place. Why sensible cooling alone is insufficient? This is a key thermodynamic question. Why can't we just cool the outdoor air senselessly to 24 degrees? There are 4 reasons shown on the left alongside the psychometric chart. Point 1. Sensible cooling is a horizontal line. On the psychometric chart, cooling without dehumidification moves the state point left at consistent omega. Starting from state 1 at omega equals to 25.72 grams per kilogram, this horizontal line hits the 100% saturation curve at the dew point 29.08 degrees, which is 5 degrees before we even reach our target of 24. We hit a wall and cannot proceed further. Point 2. Outdoor moisture far exceeds the target. Omega is 25.72 grams per kilogram, but omega is only 10.24. That's 15.48 grams per kilogram of excess moisture. A change in temperature cannot change omega. You cannot remove moisture by cooling alone. Latent heat removal is mandatory. Removing water vapor from the air requires condensation, which extracts the latent heat of vaporization, approximately 2501 kilojoules per kilogram. This only happens when air is cooled below its dew point onto a cold coil surface. Sensible cooling by definition cannot do this. The two-stage process is only valid solution. Step 1. Cool and dehumidify the ADP at 14.4 degrees, removing the excess moisture. Step 2. Reheat sensitively back to 24 degrees. Together, they reach state 3. Sensible cooling alone never can. On the chart that you can see the correct path, diagonally blue line from state 1 down to state 2 at the ADP, then horizontal orange line across state 3 inside the comfort zone. To conclude, in question 1, the 100% fresh air system requires a total AHU load of 149.8 kilowatts, 128 kilowatts of cooling, and 21.8 kilowatts of reheat, removing 2.058 kilograms of moisture per minute. The key driver was the outdoor dew point of 29.08 degrees, forcing dehumidification. In question 2, the mixed air system at 30/70 reduces the cooling load by 57.4% to 54.5 kilowatts, saving 73.5 kilowatts and cutting the total AHU load by nearly half. This comes with trade-off: CO2 risk, filtration requirements, and ASHRAE 62.1 compliance. But it's the correct engineering approach with proper safeguard. The fundamental thermodynamic insight: sensible cooling alone is insufficient because the outdoor dew point exceeds the supply temperature, making latent heat extraction through condensation unavoidable. Thank you.